Swayam Prabha. Digital India. Educated India.
Welcome back. So let's look at the 1, 3 and 1, 4. We did the 1, 1 and the 1, 2 earlier. This is just to give you some more practice. So we have 3 ways of drawing right now. One is like a head-on or cyclohexane, like a flat 6-membered hexagon structure, and we show things that come towards you with a wedge and away from you as a dash. So here's a 1, 3, and you can see they're both coming towards you, so therefore it's going to be cis. So if you have a cis cyclohexane, you would draw both of those as either both wedges or both dashes. So here, let's say this is that's cis, or you can put both of them as dashes, as long as they're on the same side. And let's say one of them is an ethyl and one of them is an isopropyl here. So there are 2 chair forms possible for any molecule that's in a cyclohexane form. One of the chairs, in this case, here's a flat. We can either have them, so they're both on peaks here, so they both would be either axial, or we could flip it and they would both be equatorial. And I'm sure by now you know which one's better, right? The axial here is going to have huge bumping. You can see the sword fight there, right? And then you can see, so there's a lot of 1, 3 diaxial, mainly with these big groups. Hydrogens are so teeny, but the big groups. And here they kind of got in their corners, they both put away, so they can't fight anymore. And this is the most stable chill out position for this molecule, the energy minima. All right, so we can draw both of them, and then we'll also draw the Newman projections for these. So 1 chair coming up for you. So here you can see that same thing, same principles as before. You draw the 2 parallel lines, then you put a dot and connect the dots here to make a beautiful chair. Then when you draw the other chair, now you draw those parallel lines facing the opposite direction. And then you do the same thing and you connect the dots there. If you do that every time, you are not going to get these kinds of chairs that we see all the time where you have a huge angle here, or you'll see things like this, they're all stretched out. So these are the stuff that we kind of see, and then here, or like that. So better, we just draw the parallel lines nicely, then the rest will come along. So let's label this ethyl, 1, 2, 3, 1, 2, 3. On 1, ethyl is facing up and isopropyl is facing up. So here you have a point coming down, the axial is vertically down. And let's see, on 3, 2, when the point comes down, axial is vertically down. The equatorial is going to be 109 degrees away from it. So 1 has got an ethyl, so it's a CH2, CH3, and we can put the hydrogen over there going down. This is an isopropyl group, and again you'll have a hydrogen there, so the isopropyl group is pointing up and your hydrogen's pointing down. So that's the one where you have them both now in very stable positions. You can see that. Now when you flip them, well, then they get into the angry position. So when you take 1 and go up, it's going to go up here. First facing up, 1, 2, 3. So we're going to have these lines coming down, and we'll have the dots parallel to that, and you have your chair. So now we have number 1, 2, and 3, and on 3 the ethyl is going up. So let's fix the axial and equatorial and the 1, 3 position before we put the groups in. So when the peak goes up, axial is vertically up. Peak goes up, axial is vertically up. The equatorial is about 109 degrees away from it. And we have both hydrogens at the bottom. And here too, the equatorial is going to be 109 degrees away from it, parallel to that bond. On the top, well, 1 has got the ethyl. and 3 has got the isopropyl. I can draw it out like this. I can just put the lines. Doesn't matter. You can see it's pretty obvious that these two guys are butting heads. It's very obvious. So that is bad for the molecule. So it kind of gets away from that. These values are bumping with hydrogen. If you're bumping with these two here, it's going to be way, way, way more than that. So therefore, the molecule is going to quickly rush back here, and maybe once in a while it just goes blip, but it's never going to be here for too long. It goes back here, and this is the chill out position. Sit in front of the TV, get it, on its favorite sofa. Now, while we're here, we can also draw your Newman projections. So the Newman projection here for the top molecule, you can see these are pointing away. The best way to look at this is through here and here, so that way you have a front row seat and you can see both your groups. So then if you draw this, these are your dots, and these groups are coming off to the side on the dots, and these are your circles, and you have hydrogen staggered to those. Let's draw this out, and you can see the number 2 carbon here is coming up, and the number 6 bar at the back is coming down. Okay, so let's draw this out. So here's your front row seats here. You're going to look through this bond and this bond. So that's where your I is. And I'll draw for you. This is your dot, this is your circle, this is your dot, this is your circle. These are the two CH2s in between that link the two butanes. So the dot here and the circle there, and dot and circle, and you will have your CH2 up joining that, and the CH2 going down joining at the back. On this carbon, ethyl's coming to a side, so you'll draw it out like that. And the hydrogen goes directly vertically down. On the back carbon, the hydrogens are just going to be axial is pointing up and equatorial is pointing over here. There you go. So this is what you just drew, this part. Now let's draw this butane part. So you have an isopropyl coming to the side, and you have your hydrogen coming down. So that's going to the side, and your hydrogen comes down. And behind that, you will have your hydrogens staggered. When you look through here, they're going to be staggered. Hydrogen and hydrogen. These two hydrogens, when you look through, you're going to see them staggered. Now, this is really good. You don't see any 1,3 diaxia. So let me write that down, since that's very important. And you don't even have extra gauche interactions due to this, because these are pointing away from each other. They're not in the same direction. Let's draw A out just to show you how bad it is. So over here, you're going to do the same thing. You're going to be looking at A through here and here. So when you look at it like that, you're pretty much going to see a dot and circle. So you're going to look at it like that and like that. So you basically look at it like this, through here and through here. So dot, circle, and this CH2 is going to be dipping down. So basically you're pulling this like a sash down. This is going to rotate counterclockwise. This is going to rotate clockwise. So pull down the sash and bring the CH2 down. These are going to be standing up. The CH2 goes down here. These are going to be pointing up. So the CH2, CH3, and the hydrogen are going to be rotated 60 degrees counterclockwise, and this will be going clockwise, because that's how the rotations will work. Then you're going to take the back carbon, and it's going up. So therefore, you will have these staggered at the back. So this CH2, we pull it up. You pull it up, like with the suspenders, you pull the guy up. These guys kind of straighten out, and you have your hydrogens over here. Now you can see there's going to be a huge fight out here, battle, duel between these two. 1,3 diaxial. So this one has no 1,3 diaxial. This one has very high 1,3 diaxial. Therefore, it's going to quickly rush back here. So this is going to be very high 1,3 diaxial between these two groups. So between A and B, B is going to be the one that would be the favored molecule, or the favored conformer. It's the same molecule, different conformers. Let's try to do a 1,3 trans. That means you have two groups on 1 and 3 positions of the cyclohexane, and they're pointing in opposite directions. If one's pointing to the sky, one's pointing to the earth. So here it is. Let's do this molecule. Here is your molecule. This is a 1,3. So you can have a, let's say a T-butyl, let's say, and a methyl. So a T-butyl and a methyl, and just to make it a little easier to see, T-butyl, methyl. So this is coming out at you, so that's a wedge. This is going away from you, that's a dash. So that's the perspective diagram. So here's the perspective with wedges and dashes. Here are the chairs, and here's the Newman. So those are the three ways in which we usually draw the cyclohexanes. So if it's 1,3 trans, you will have, let's say, a group here and a group here, 1, 2, 3, in the opposite directions. We can draw the chairs for this the same way as we have drawn the chairs before. We put two parallel lines, then we connect the dots and make a chair that will show off all of the angles. So here, important thing is to label the carbons on which we are going to put our substituents. On 1, we have a T-butyl. On 3, we have a methyl. So if you take this chair, you can see that if you draw your chair like this, the T-butyl is coming off on a side and the methyl is pointing down. So let's draw that out. What's up is always going to be up. In this case, we're drawing it equatorial. What's down in 3 is going to be down. 3 down, because the peak is going down, the axial is going to be vertically down. And they would be in the same place. I'm just going to label this CH3. So here's a group. Yes, we do have some 1,3 diaxial here, which is about 7.6. But this group is away, and there's no 1,3 diaxial from it. So if it's equatorial, you're not bumping into groups that are parallel to you, because there are no parallel groups. If you take the hydrogens here, they're staggered, you see? So therefore, this is really nice. Let's see whether the other one is better or worse. So we're going to flip this. We're going to turn this up and turn this down. So here we go. Turn this up and turn this down here. So you can see now your T-butyl group is up and your methyl's off on the side. So let's draw this out, guys. So here you do the same thing, except now your parallel lines are going in the opposite direction, and you will draw them out like that, and then you will mark 1, 2, and 1 and 3 carbons. It's better to first put your lines and then put the groups on. So peak going up, axial is vertically up. Peak goes up, axial vertically up. And draw the equatorial parallel to this. Draw the equatorial parallel to that. So here on top stays on top. Top stays on top. This is your hydrogen, and here's your methyl. What do you think about this? Bad, 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 isn't it? Because you got this huge electron cloud, which is 3 methyl groups, then doing a lot of bumping with these. So that's a lot higher, 22.8. So here we did this over here with the chairs. Let's do the Newmans. So pretty much the same way, 1 like we did here. You're going to look through 1 and 3. So between this carbon and this carbon, and this carbon and this carbon. So now that I've been showing you these models, we can just do them without them. So here we're going to look at through this bond and through this bond. Okay, that way we have 2 butanes here that we can really look at. So let's say this is B and this is A. So if I do B here, that's your dot and your circle. Dot and your circle. So that's the circle at the back here. This is the dot and circle here for that. You can see your CH2 is going up here in the front. And then on here, the T-butyl is on the side and hydrogen is below. On here, hydrogen is on the left and methyl is going down. At the back here, you do the same thing. Your CH2 is going in between there, below. The peak is below there. And the hydrogens over here are going to be staggered because they are going to be in between these groups. So that's your hydrogen there and your hydrogen there. That's staggered. So you can see that, well, the hydrogens are staggered and staggered. CH2 up in front, CH2 back at the bottom. This is your T-butyl group. This is your methyl. All right. So let's try to flip it to the other chair now from this one. So if you go up here and go down here. So now you can see T-butyl is vertically up, the back hydrogens, and you're going to look through here, dot, circle, and dot, circle. Methyl's on the equatorial down, and T-butyl is on the axial up. All right. So basically bring the CH2 down. These are going to rotate counterclockwise, and these are going to rotate clockwise 60 degrees. So here are the dots and the circles. So pull the CH2 down like a sash. That'll rotate these up. And hydrogen. And same here, this is going to rotate this over here. And if you pull the back CH2 up like a sash, that's going to rotate these 60 degrees counterclockwise and these clockwise 60 degrees. So here is your back CH2 pulled up, and these are going to be completely staggered, which is how we like them. And which one do you think is better? I'm waiting to hear that. All right. You can see there's a huge electron cloud here with the T-butyl, and so you have a big 1,3 diaxial. Large 1,3 diaxial. Well, over here, we don't have that because it's out of the way, but this methyl group and this hydrogen will be bumping, but that will be a small 1,3 diaxial. Okay. And this is going to be your small 1,3 diaxial. And then in terms of energy, this is about 22.8 kilojoules per mole higher than this is going to be about kilojoules per mole. So that's about 13.6 kilojoules per mole difference between the two of them. We may have done something similar, and then it's about 99.5% here and about 0.5% here. So this is huge compared to this. So this is where we want to be and not here. All Right, so between B and A, you want to be here and not here. All right, so that's 1,3 cis and trans. What about 1,4 cis and trans? What do you think is going to happen when we move these things one carbon away? Again, you can move them so that they're both on the same side. So this, and let's say I put an ethyl group here. So that's going to be cis. You can draw it like this or like this. It doesn't matter. It's the exact same molecule. You have, actually you can see a plane of symmetry running down. So whether you draw it here or here, it doesn't really matter. So now, what are the possibilities for this molecule? Obviously, you don't want a boat. All these other twist boats are all higher in energy. Chair's the best. Do you want a chair where your T-butyl is up and your ethyl's to the side, or equatorial? Or do you want the flip chair where your ethyl is axial and your T-butyl is equatorial? Which one do you think, guys? It's pretty much here. Here, this is huge. This group is really huge. So it's really going to get away and go to this small group being up, right? So let's draw this out as the perspective with this and this coming out at you as a wedge. So here is a perspective diagram, T-butyl coming at you and ethyl coming at you. Or they can be both on dashes. It's the exact same molecule. Now, let's draw the chairs for that. Again, same principles as before. Put the two parallel lines and then you connect the dots there. And then you make your chair. And now you can put your vertical lines and your equatorial lines at the positions where the substituents are. 1, 2, 3, 4. You don't have to show all of the hydrogens, but it's good to show the hydrogens where the substituents are placed. So on the 1 and the 4. So before you put in all of that, label your chair and put the axial and equatorial in the right places. Peak coming down, axial vertically down. Peak going up, axial vertically up. Then the equatorial is going to be about 20 degrees above the horizon, and here too. Now these are coming out at you, so if you're going to look from the top, you will see them on the top bonds. So this is going to be 1 has got a T-butyl and 4's got an ethyl. The hydrogens are below, so this is a top-down view. So if you look at it like this, you should see this. And here's your hydrogen. So that pretty much takes care of one of the chairs. Well, you can see there are hydrogens here, and you will have some 1,3 diaxial bumping. Between the ethyl and the methyl, the difference is only 0.4. That's because the CH3 will always be pointing away from these hydrogens. So it's basically this carbon, the CH2, that's close to that. So let's look at the flip chair. So, and here you're going to put this up and bring this down. Basically, that's how you're going to flip the chair. So you are going to take this and you're going to bring this up and bring this down. So 1 up and 4 up, but one's equatorial and one's axial. So let's draw the chairs. These parallel lines now would be going in the opposite direction. You put your dot and a dot, and you will connect these dots to make your chair. On this chair, you again number the chair where your substituents are, and before you rush in and put those groups, label the axial and equatorial. Peak going up, axial vertically up, peak going down, axial vertically down. Your equatorial's got 109, like 20 degrees below the horizon. And now go back and see where the groups are. Up, up. So if you're looking at it from above, you should see this up and this up. And the hydrogens will be hiding below them. So there's your chair for the other flip one. And here you can see this is going to be huge. You can see that's going to be a lot higher. This one's out of the way. So between the two of them, you would prefer, I would think, This one, this is about 22.8 kilojoules per mole, higher than a cyclohexane. This is 8.0 kilojoules per mole. There won't be any gauche either because this and this is anti, this and this is anti, so you don't have gauche interactions. Well, let's look at these molecules from a Newman perspective. So here, let's draw the one above. So that's your molecule. You can look at it like this. These are the dots, the front dots. These are the circles. Here you have the second carbon coming up, and the carbon number 5 over here is going down. You're going to look through 1, 6, then you're going to look through 3 and 4. So this is where you're going to place your eye. You're going to look through 1, 6, and you're going to look through 3, 4. All right, so that's your dot, that's your circle. So let's draw, let's label this C, D or something. This is your C, dot, circle, and dot, circles. This is one butane, and this is your other butane. Let's draw this butane out first. Here's your dot, and behind that's the circle. Here's your dot, and behind that's the circle. Now your CH2 here is going up. That connects the two dots, 1 and 3. This is your 1 and 3 carbon. So this carbon that's number 2 is a CH2, and that is going up. And the one at the back, CH2, is going down. That makes it easier to place the others because this is going to be like a Mercedes-Benz symbol. So you have 1, 2, 3 things on that carbon. One of them is the CH2, the other is a CH, and the other one is a T-butyl. Same here. You have 2 hydrogens here, and that's what you're going to put on that dot. And you're going to look through here. At the back, you're going to see the ethyl pointing up. CH2, CH3, and a hydrogen that's going to come on the side at the back. Over here, you will have the same hydrogens at the back, and they will be completely staggered. So you can see there is a 1,3 diaxial here, and that's not too much. It's like 8.0. So now we can draw the other one where we're flipping this to the other chair. So now this is up and this is down, and we're going to do the same thing. We're going to look through here, and we're going to look through here. These two where I'm holding. That's the carbon. So the front, what you see is the dot. Behind that is going to be the circle. This is the CH2 now coming down. The back CH2 went up. Basically, you pull this down and you pull the back carbon up. So you have the same dot, circle. Once you draw this, sometimes it's easier to draw the other one from here. So bring the CH2 down, and that's going to rotate the groups counterclockwise 60 degrees. And clockwise here. Pull the back carbon up. So you're going to take this and pull it up like a sash. That's going to then rotate these hydrogens clockwise. And this one is going to go 60 degrees down. And over here, when you pull the back up, this back carbon will rotate 60 degrees over here to counterclockwise. And now it's really obvious that this is going to be bumping into this hydrogen, and these hydrogens big time. So there's a 1,3 diaxial is 22.8 kilojoules per mole. There are 2 of them, but one of them is on one of the CH2s here, so which is why we're not really showing that. So there's 2 of them over there, one here and one here, 2 1,3 diaxial interactions. all of that is 22.8 because we're comparing it with a cyclohexane. Let's do one more. We'll do a 1,4 trans. So you have, let's say, an ethyl coming at you, isopropyl going away from you. So this is going to be on a wedge. This is going to be on a dash. All right? Okay, let's get on with it. Let's draw it out. 1, 2, 3, 4. And one has got a isopropyl coming at you or above the plane. If I hold it up like this, and this is below the plane. So let's draw the chairs. Draw the chairs like we did before. 2 parallel lines and connect the dots here. So now we can take this and we can draw axials and equatorials where the substituents are. So 1, 2, 3, 4. So let's put them down first. So peak going down, axial vertically down. Peak goes up, axial vertically up. Now the equatorial is going to be about 20 degrees above and below the horizon. Now let's put our groups down. We have an isopropyl on one. On the top carbons, when you look at it from here, it's the same as looking at this. So you will see this popping up, and you will see this away from you. And then you'll have the hydrogens on the opposite side. Now, this one, well, it's really, really good. This is away to the horizon. This is equatorial. There's nothing bumping in with these axial hydrogen. So no 1,3 diaxial. This is pretty much where it's going to be, guys. You don't even have to bother about writing the other one because it's almost never going to get there. But once in a while, maybe it gets excited and goes up to the other chair, which is, well, showing you on the models here. So this is your di-equatorial. Flip it. And obviously equatorials become axial, so the diaxial over here. And these lines are going to go down here, put the dot and connect them, put the dot and connect them. And now you're going to again label 1, 2, 3, 4. And before you put the groups, mark the axials vertically up and down at the peaks, and equatorials 109 degrees away. So on top is your isopropyl, and at the bottom is your ethyl. Here, that's your hydrogen, and pointing up is your hydrogen. So the directions don't change. It's the axials become equatorials, and the equatorials become axial when you flip it. All right, so now you can see this is going to be a huge problem for this molecule because these 2 hydrogens are going to be bumping into this ethyl over here. And these 2 hydrogens are going to be bumping into this even bigger monstrosity, this isopropyl group here. So that's really a very high. So that's 9.2 for that and 8.0 for here. So that's about 17.2 kilojoules per mole. That would be more than 99% on this side. So delta, when you say the difference, you would put for this delta G, you would put 17.2 minus, so minus, and you can use that to get your difference. Let's look at your the Newmans here. So for the other one here, where you have these on the side, again, you're going to be looking at this and this. CH2 coming down at the front, CH2 going up at the back. So over here, you're going to look at this and this. So dot, circle, dot, circle. Let's draw that out. And here on the dot, the CH2 is connecting them up, and the other CH2 at the back is going down. And over here, you are going to have your, on 1, isopropyl to the side and hydrogen down. Behind that, on the carbon 6 at the backs, the hydrogens are going to be staggered, hydrogen and hydrogen. On 3, you have nothing but hydrogens, so and hydrogen down and to the side. When you look behind, you'll have a hydrogen pointing up and an ethyl falling off to the side like this. This is the most stable because you can see there's no 1,3 diaxial with big groups, just hydrogens. So that, let's call that X and Y. And then let's look at this one. Y is going to be same thing as before. You're looking through here and here. Same carbons as before. 1 and 6, 3 and 4. So you're looking at it like this pretty much. Let's draw that out. Dot, circle, dot, circle. Or you can go from here. This is going to be coming down. Let's draw the dots and circles. The CH2 gets pulled down, and the CH2 at the back goes up. And so when you pull this down, these are going to rotate up 60 degrees. And you can put this, when you pull this down, these will also rotate upwards 60 degrees. When you pull the back carbon up, then these go 60 degrees clockwise. And these will go 60 degrees counterclockwise. And there you go. And you can see now you will have a hydrogen, and there's a CH2, CH3 here at the bottom. Now, over here, you can see this is an electron cloud. You're going to be bumping into that hydrogen. Here's another electron cloud here, bumping into this hydrogen. Really bad. So this guy is going to go up here and be happy as a lark because it's got nothing and nobody in the way. So here's where you're going to be chugging your a beer or whatever and nuts and sitting out there chilling out with your friends. Once in a while you get a little hyped up and then you go over here and back again. This is your natural energy minima state. So this is your energy minima. It's more stable by about 17.2 kilojoules. That's a lot for more. So in summary, I'd like to say that if you have substituents on a cyclohexane ring, they prefer to be equatorial. When they're axial, they have 1,3 diaxial interactions, which make them unstable. So here's the Newman projection. It is a head-on view, and you can see in the Newman projections when these are equatorial, there is no bumping. But when you draw Newman, you're taking the CH2 in the front and bringing it down, and you will see that these are rotating 60 degrees up counterclockwise, and these are rotating 60 degrees clockwise. So 60 degrees clockwise or counterclockwise depending on where they are. All right, so another thing that I'd like to point out is when we write out our equation, we are going from less stable to more stable in our K equilibrium definition. So in here, the B is your product, A is your starting material in a reaction, but this is not a reaction, this is just a rotation. But even then, we will put the more stable up and the less stable down. That way, when we plug them in, so the delta difference in energy here would be a negative, and when we plug it into that equation, negative times negative will be a positive. Therefore, you will have a higher percentage of your stable product. Conformer that's more stable on top and the conformer that is less stable at the bottom. All right. And please make sure that you watch the previous one before you watch this, and let me know if you have any questions. Bye.